chairing, Tom, right?
No, your chair.
I'm the chair.
Yeah.
Right.
And another confusion.
I can check the website if you
Oh my
want.
God. Lars, can you change the website again, Lars?
Yeah, I can. Yeah, easily.
Okay. Yeah, what an honor. So I think it has been said all. We celebrate 1 year of VPOS. Maybe it's just the beginning of a long story. Hopefully never or not too soon ending. And to celebrate that and to show that we last longer than COVID. And maybe VPOS will also see the re-entry of the British Empire into the EU. We don't know, maybe. So let's just hold on. And I think there's only one person we can celebrate this event with. This is John Simpson, whom most of you know. He is a scientific heavyweight, I would say, in terms of coastal and estuarine oceanography, in terms of theory and observations, and of course also he was participating in many modeling exercises. And he will not talk about the coastal ocean today. He found a new hobby, and that is lakes. So John will tell us about Lake Windermere in England. So John, the floor is yours.
Well, thank you, Hans. I'd like to express my thanks actually to the organisers for giving me the honour of giving this first anniversary celebration of the VPOS series. I think everyone recognises that the series has been a very big success, and it's provided a lively forum for the discussion of new developments in physical oceanography, initially in Europe, but now sort of worldwide. It's been especially good for me, keeping me in touch with the physical oceanography community now that we're living in Harrogate in Yorkshire, a town not known for its concentration of oceanographic-minded people. My talk today is about some of the results from a year-round study of physical processes in Windermere, as Hans said, in which we enjoyed some rather surprising and to me slightly amazing touches of serendipity in what we found. It really wasn't what we anticipated at all when we made the plans for a rather ambitious 15-month study of the lake. The study was in collaboration with the Centre for Ecology and Hydrology in Lancaster. And I think I'd better put my first slide up now so you can see who my co-participants were. See if I can find the share screen thing all right. Here we go. Okay, do you all see the full screen slide now? So what I want to show you just on this is who the key participants were in the project. The link with CEH was mainly through Stephen Madeley, who's well, he's a sort of biogeochemist in limnology. And he's been instrumental in getting us all together to work on Windermere. The key, the most important two people in the author list on the paper are Iestyn Woolway and Brian Scannell. Iestyn actually, I think, should take a lot of the credit for instigating the study. He's a real enthusiast for physical studies in lakes, and he persuaded me and others to get moving on this. Brian made important contributions to the data processing, as did Yestin as well. And oh, the other person I should just mention on there, he's no longer with us, and that's Phil Wiles, who was at Bangor and who helped us when we were writing the code to use the structure function method, which we use for the dissipation measurements that I'm going to talk about. Okay, well, let me just start with something that most of you will probably know already. This is a simple sort of paradigm of the way that lakes work. Lakes, unusually for me, don't have any tides, at least not any significant tides. And they get all their energy, or nearly all their mechanical energy, from the wind. And the wind is not really very well adapted to putting energy into the lake. If you look at the amount of energy in the boundary layer of the atmosphere and see how much of that actually gets into the water, it's about 1%. So the lakes are rather energy deprived, and they are therefore some of the most tranquil environments. I think actually the reason we went to lakes in the first place was to find a very tranquil environment in which to test our techniques for measuring turbulence. Now the big thing that sort of in a way kind of apes the tides in the ocean is the group of seiches, the internal and external seiches. External seiches operate year-round. Internal seiches only operate during the stratified summer season. And you can see from my little picture here, this animation, that seiches are energizing the whole water column. Although the energy goes in through the surface, and a lot of it is actually used up there, the seiches actually transfer a lot of the kinetic energy down and provide for a much more energized water column than you'd have in the absence of seiches. And that, of course, that input of energy is what's powering the dissipation and the all-important mixing, which is the key link really with the ecosystem world, where these processes are very important influences on the ecosystem. In areas like the transport of nutrients, for example, across the picnic line, and in the redistribution of greenhouse gases, notably methane, which there's a lot of methane produced in lakes, and its escape from the lakes depends a lot on the processes of mixing in the lake. So that's the sort of background, and what our project was about was trying to clarify some key components of this sort of outline model of the way the lake works. The first thing actually was to see how much energy gets put into the lake, and that we have done now, I think, fairly convincingly. It varies a lot between the winter and the summer, not much. In the summer, about 1% is a fairly good figure for the amount of energy getting into the lake from the atmosphere. The second question was about the seiches and which ones are dominant and when and so forth. And the third one, which is what I'm really going to talk about, is how much energy is dissipated in the picnic line, the boundary between the surface layer and the deep layer, what the limnologists call the hyperlimnium. And I'm going to look at the bottom of the hyperlimnium, at the bottom boundary layer, which has always been canvassed by limnologists as a major sink of energy. So here's the Lake Windermere. Actually, this is half of the Lake Windermere. It's twice as long as this. This is about 11 kilometers long. It's the Windermere Southern Basin, it's called. The reason it's treated separately is there's a very shallow sill, about 2 meters deep, between the two lakes. And that little dotted line there shows you roughly where the sill is and is the boundary of the lake. the dynamics are only very slightly coupled. And so we're dealing with essentially one rather narrow lake here. And there's the position of the mooring buoy, which has all the Met instruments maintained by CEH. And we put our instruments there close by. One sort of big spread of ADCPs in the middle of the lake. And I'll just tell you what was there. The thing over here on the left is a thermistor chain, actually a set of loggers. I think we started the year with 20 of these and we finished with about 17. We lost one or two during the action. Then we have 4 Doppler profilers, all doing slightly different jobs. This one is operating in pulse-pulse coherent mode, which I guess many of you will know gives very high resolution in velocity. The noise level in these pulse-to-pulse instruments is millimeters per second, usually 2 or 3 very, very accurate velocity measurements. But the trade-off is against range. You have a lot more range, a lot less range because of the pulse-pulse operation. This is another pulse-pulse one here on the bottom, which measures only a span of about 4 meters in the bottom boundary layer. Sorry, I forgot to say this one has a 7-meter span. It's better, interestingly, because the frequency is lower than this high-resolution one. And then this one is sort of monitoring the dynamics over the whole water column. About 85%, you know, you lose a bit at the bottom and you lose some at the surface because of the acoustic beams getting mixed up at the top. And then we added a 4th one to give us a view of the surface. We're going to calculate the energy input from the stress imposed by the atmosphere and the velocity right as near to the surface as we can get. And by having this extra one, we were getting within about 1.5 to 2 meters of the surface. So the plan was for a full seasonal cycle with an overlap. So we started in October 2016 and we went to December in 2017. In 5 deployments, we had to have a small number of deployments because we didn't really have a lot of money to do this job with. It was largely support from the 2 labs that enabled us to do it. And we had to go sometimes for as long as 100 days, which of course meant compromising on storage and things. But as you'll see, we got pretty good coverage the whole year. Now, to make that clear to you, I'll just show you a big panel with essentially all the data that we collected. This is the surface stress monitored in the middle of the lake by the buoy. This is the temperature structure monitored by the temperature chain. And you can see it shows the sort of classical pattern for lakes of stratification developing from just after the vernal equinox. I think I've lost some little green things off the top of the screen here. I don't know whether you're seeing them. They're meant to tell you where the key points in the annual cycle are. That's the vernal equinox. There should be one for the summer solstice hiding behind that panel. And then there's the winter solstice over here. Let's go back one. The next panel down here is perhaps one of the most visually striking. It's a picture of the axial velocity in this rather narrow lake. Most of the energy actually is in the longitudinal, the axial component. While the lake is stratified, is mixed as it is during the winter, the structure is rather diffuse here. And the kinetic energy, which is shown in this lower panel, is very small. Here you see, just after the onset of stratification, that the modal structure starts to develop and really dominates the flow. And the kinetic energy at that point starts to increase, on average by a factor of about 5 into this very, very active period in the first half of the summer. It tails off a bit later on and eventually drops back down to very low levels, as you can see the picnic line here dropping down too. But the highest velocities actually you'll see are associated with the picnic line. And what I'm really going to talk about is not those things, but this stuff at the bottom here now, which is the dissipation records in the mid-water, we have to say. The mid-water here means the picnic line when the lake is stratified. That's really those two big deployments. You see the gaps where the instruments were serviced. That's the one in mid-water or in the picnic line, and this is the one from the bottom boundary layer, between 1 meter and 5 meters above the bed. Quite on top of this yet. One thing I have to tell you is how we actually use the ADCPs to make estimates of the dissipation. We do it by the technique which we call the structure function method, after the structure function, which you see here came from Kolmogorov in 1941. The key thing is that this structure function is made up of velocity differences. They're actually the turbulent velocities, so the mean has been taken out. And we're taking differences between different bins along the ADCP beams and squaring the difference between those two beams as a function of their separation R. And that's what we mean by, I suppose, this is what they call a second order structure function. You can have higher orders as well. We're using the second order. And once you've got it, then you're really onto epsilon, which is the dissipation, which goes as epsilon to the 2/3 and R to the 2/3. So if you plot the dissipation against R to the 2/3, you should get an estimate of the dissipation, subject only to this constant, which is actually well known. Now, we actually recover it by fitting the observed dissipation, the observed structure function to R to the 2/3. And this is examples of that being done. And at different dissipation levels, you get the fits like this. There's an interesting feature that at zero separation, there is still, of course, a difference, because you're looking at the Doppler noise there between adjacent bins. And that's actually a completely independent way of testing whether the manufacturers of these things are telling the truth about their instruments. I should mention here a credit to the meteorologists. Actually, I got the idea of using structure function methods for turbulence from a French meteorologist called Michel Crochet when I was working in the university in Toulon. He's a radar meteorologist, and he uses all the same kind of formalism for his radar beams as we do for the ADCP, for the acoustic analog in the ocean. Okay, well, I think that's more or less all the preliminaries that we need, but I'm just going to show you how we measure the total energy input. Can I get rid of this panel that's jumping around on my screen? It's like photographs of people, I guess. anyway, the idea is that you want to calculate how much energy is going into the lake. And you do that by taking the product of the wind stress, which is assumed to be continuous across the surface. We measure it in the atmosphere, but we assume it's the same in the top layer of the ocean. And we multiply that by the surface velocity. So it's the rate of working, strictly, that we're looking at here. How much work is the atmosphere doing on the ocean? And when you product those two together, you get a plot like this, which, as you see, is almost all positive. There are times when the wind is actually opposing the surface current, and then there is a negative effect. But such events are rather few. It really surprised me when I first saw this. Okay, well, that's how we get the reference energy, the total amount of energy going in. Now I'm going to show you how much energy is being used up, first of all, in the picnic line. How much dissipation is there in the picnic line? And this is a sort of summary picture of the picnic line for the summer season. It starts to form actually a little bit before this, because I haven't set the threshold for gradients. You can see this is actually the parameter n squared, the stability frequency squared. And it starts to show significant gradients in about day 110. And it has a rather chaotic sort of development, and you see it here, depending, of course, on the mixture of solar heating and wind stirring that's going on. And we tried very hard to capture what was going on in here with our limited range of 7 meters. The first time we didn't do well at all. That's what we call the picnic line box, which is it wasn't 7 meters. We only managed to get 5 meters the first time. Quite good data, but as you can see, it was only a subset of the whole picnic line. You know, would like to have seen a much bigger coverage there. Fortunately, though, later on in the summer, when we got to the next deployment, things were much better. The whole thing had tightened up, and we actually placed our instrument in just the right depth range to see the central region, and indeed most of the picnic line for about 80 days, I think it was there. So this is the data for the picnic line, which I want to concentrate on because it covers the picnic line well, and is likely to be representative, I hope, of this sort of period of the year in lakes like this. The other thing was the bottom boundary layer. We have a box there, which was just between 1 meter and 5 meters above the bed. We'll come back to that. First of all, I want to show you the results from deployment 4 in the picnic line box. So there's the reference energy input at the surface, RW, and here's the total dissipation in the 7 meter span in the picnic line. And you see it's highly variable, as of course is the input. And the whole background for this is that wind forcing is extremely erratic and unpredictable and concentrated very often into short, fierce bursts. And so is the dissipation, as you can see here. If you go along the peaks on here, you'll see they all match up pretty well. Sufficient, I think, to convince you there's a fair amount of coherence between the two. So we tried a regression analysis on this, and it works very well. This is actually the neutral regression, since we couldn't convince ourselves there's more noise in the dissipation or in the rate of working. And the neutral regression amounts to 3.5%, roughly 3.4% of RW being consumed in this span of this 80 days. It's more like 100 days here, isn't it? Of so total dissipation only 3.5% of RW, which is rather little. If you look at the spread of the data, if you plot, instead of the integrated dissipation, you plot it as a function of the depth over the 7-meter span, you see obviously the same prominent features in the yellows here, which is the top of the contouring range. But you also, I was very surprised to see this and couldn't explain it at the time, but there's a kind of periodic stratification, a sort of ghostly thing going on behind the scenes when there's no wind mixing. You see these things everywhere, and they look curiously regular. And some of you might actually figure out what that is, but I didn't when I first saw it.
So, John, one quick comment. You are sometimes a bit far away from the microphone. You need to speak up a little bit because sometimes things get lost. Sorry.
Oh, I'm sorry. Okay, I'll try and get closer to the microphone. So here we are looking at the Picnicline again, or the, I should say, intermediate waters, because here this is in the mixed regime during the winter. You know, take that out of the way, you can see the vernal equinox is here, and stratification starts very soon after that. And when it does so, the coherence between the wind forcing and the dissipation in the Picnicline remains pretty much the same. You see it's actually quite coherent here all the way through. I guess you could do the same sort of regression there as we did in the other data. But I'm just showing you this to give you a contrast with what happens in the bottom boundary. If you go down to the bottom boundary there, then things look very different. And you see this sort of thing, where so that is not reflected, this is not reflected very much in the bottom boundary there. And yet there are rather large changes in the dissipation, which is obviously periodic in some way. If we blow that up, say in that box, so what's that? That's about 60 days of data. Then what you see is this. And that is obviously periodic, and more than being periodic, it's periodic at exactly a period of 1 day. It's a diurnal oscillation. We're 40 meters down in the lake, and the dissipation is going up and down every day by, what is it, almost 2 orders of magnitude. And here you may start to question what our interpretation, but I hope I'll convince you. One thing to note straight away is the phase locking of this. These tick marks on the x-axis indicate midnight, and it's the usual convention in MATLAB. And you see that there's a minimum coincident with midnight. Look again here at 1:30, the same again. There's one missing there where the oscillation seemed to hesitate for a moment, but it's back again here. There's a minimum spot on 150 and at 160. So what do you think? What could be causing a large diurnal oscillation in the bottom boundary? And you might think, as I did, well, what about the diurnal winds? We know that lakes very often have quite a peak in the spectrum in the diurnal band. So could it be that a seiche of diurnal period is actually driving this effect? Well, we've only got to think about it a minute to see that it can't be that, because if the seiche is diurnal, let's say the water is flowing to the north in the lake, you would get a maximum in the dissipation. When it turned around and went to the south, you'd get another maximum. So you would you would only generate a 12-hour period in dissipation from a 24-hour safe. So it isn't that. You'd actually have to have a 48-hour period to get in the velocity to get a 24-hour period in the dissipation. So now here's a clue. This is a bit of data which we had as a byproduct, really. This is the echo intensity data from the water column ADCP. And you can see it has a very regular phase-locked dissipation cycle in it. The question, of course, is how would that link to this? If I do the same trick again and extend out this period here, which has about 7 or 8 days in it, I think you can see pretty much what's happening. This is a cloud of something, some organism descending, staying in the bottom layer around the middle of the day, and then as night starts, they shoot back up to the surface, and then they come back down again here. And notice the complete congruence of this pattern every single day, and its inverse is what the dissipation is doing. In fact, even more amazingly, the maxima in the concentration here seem to be actually influencing the pattern of the dissipation. It's probably over-egging the omelette, but the coherence here between the vertical migration and the dissipation is pretty impressive. And it doesn't stop there. That was during the early part of the summer. But here we are now in middle to late summer. There's the summer solstice, and there's the autumn equinox. And it's not as dramatic a swing. It's only maybe 1.5 decades. But it's still clearly diurnal when you put the vertical migration signal, the backscatter, on the same scale. You see that, well, you can't see because the scale is too big. But I'm going to show you there the actual 5 meters of dissipation measurements in the bottom boundary layer. That's what's integrated at the top. But when you see it as a vertical profile, you can see that the structure in here is actually reflected in these tongues of higher dissipation going down towards the bottom. And of course, that's just the opposite of what happens in a law of the wall boundary layer. In the law of the wall boundary layer, things increase towards the bottom boundary. So 1 over Z dependent. And here we're seeing the dissipation going up as you move away. So this doesn't have the trademark of a physical form of dissipation. So let's expand again and see that in detail in this later part of the summer. And it's the same story. The swings aren't as big, but it's when this is the echo intensity. When whatever they are, we think, of course, they're zooplankton. When they're there in numbers, then we see a maximum. When they go up to the surface, we see a minimum, and so on. Very much the same as before. But in this data, I've got something else which may help to convince you. And that is that in this case, we had an ADCP doing the water column job, which had a slightly better signal to noise than the other one. And this is a plot of the vertical velocity. And note the scale. The scale is from -1 centimeter a second to +1 centimeter a second. And if you look carefully, you can see these little, this little track of yellow dots making its way up the water column and arriving there just in time to meet the minimum in dissipation. That's when all the zooplankton have deserted the bottom boundary layer and gone up to the surface. When they come back down again, then you see a maximum and so on. And that pattern is, well, like the other one, extremely regular. And then one last point, which I think really is the clincher. I showed you those ghostly patterns in the pycnocline. Just those vertical striations, remember, very regular. They, of course, are diurnal as well. And here I've plotted the dissipation, the integrated dissipation in the pycnocline. It's a much weaker signal, but notice that it's in antiphase with the signal in the bottom boundary layer, all the way through. So that is, as we interpret it, that is a manifestation of the zooplankton reaching up into the pycnocline and maybe passing through on their way through the pycnocline to graze or whatever they do up there in the near surface layers. Okay, well that's just about the end of my story, except for one final twist. I was puzzling over ways of separating these two forms of dissipation, the physical and the what we call the biogenic dissipation. And you probably saw from one of the previous slides that the dissipation increased towards the top of our measurements in the bottom boundary layer. Here I've plotted the top bin against the lowest bin, which was at 1 meter. And the difference is dramatic. And of course, that means that there's not very much biogenic stuff going on in the bottom layer. So I made the bold assumption that this blue curve, the lowest bin, is actually mainly physical. And so we can make a guess at what the physical profile looks like by using the law of the wall to extrapolate this one value up and down through the water column. I'll show you the maths of that briefly. Here's the lake bed. Here's the lowest bin that we're recording. That's the aqueduct span of just about 4 meters. And this is the top bin. We've no knowledge of anything above that, but we do know that the dissipation is falling rapidly as you go down. It's typically a decade and a half lower down here than it was at the top, because the bugs don't seem to go that close to the bottom. So, how does it work? Well, we extrapolate from the bottom layer down to the bottom, and we extrapolate upwards to the top bin. So we then see a sort of typical curve of the law of the wall increasing towards the bottom boundary. We're putting in the law of the wall, but substituting for its value at the lowest bin the actual measurement that we made at that level. And so we simply integrate from the bottom, which is the bottom length scale, the reference length scale, and that integrates up and gives us a plot of the law of the wall energy and dissipation, which we regard as purely physical. And then you can do, as that's the result of that, you can see this, the shape of this thing actually coming through in here. I mean, that doesn't prove it's physical, but you can see these items were standing out anyway against the biology, and so it looks like that's working okay. The other thing, which is very a complement of that, is to take the measured dissipation apart. And this is measured between 1 meter and 5 meters, the same again. And we're going to take from it the wall contribution between those two limits. So we're just taking the measured dissipation and subtracting an integral of the law of the wall dissipation between the green layer and the blue layer, using again the measured dissipation at the bottom layer. And when you do that, we get a picture like this, where it really goes right down to, well, the noise level actually I think is just below there, about -6.3 or something. But there's hardly anything left that isn't oscillating now. We've dragged that out in the physical world. So the summary of that attempt to separate the two is shown here. We have this very strongly oscillating biogenic component, and we have a rather steadier and rather noisy, I suppose, dissipation of a physical kind. When you look at it, you think that the biogenic is actually the bigger part, but it isn't, because it spends half of its time down at the very low levels. And when you take the ratio of the means here, the bio is only 35% of the total. Okay, well that's it. That's conclusions time. There's only one big conclusion, of course, and that's that we've I think made a strong case for biogenic dissipation by vertically migrating zooplankton, contributing significantly to the dissipation in the bottom boundary layer in the summer stratified regime of Windermere in 2017. As far as I know, nobody else has done this, and we haven't done it anywhere else. So we don't know whether it's a regular feature in Windermere or whether this was a rather extreme example and whether it occurs in other years. The evidence basis for that, I think you probably picked up those three key points. The other conclusions about the dissipation are, I think, rather less striking. But we have established that the biogenic component is about a third. It's not dominant in overall in that long serial I showed you, the 100 days, but it is at times it is dominant. It completely outflanks the physical dissipation. And finally, if you add together the dissipations from the picnicline and the bottom boundary layer, you get between 7 and 12%, which is a pretty small fraction. It leaves a lot of room in the budget for other dissipative sinks to be found. The limnologists, I think, have always, well, not always, but recently, felt that the additional dissipation is probably going on at the ends of the lake, where the bottom is sloping gently and looks like a beach to the internal wave modes, to the seiches, when they get to the end. So the anticipation is that if we were to repeat this sort of exercise in those regions, we would find enhanced dissipation. I think there have been trials, some of the Swiss group working on this have actually tried to measure this, and I think we're well, I'm not sure I'll be involved, but I think people at Langer may be involved in making further measurements in the near the ends of the lake to see whether we can demonstrate that. And then I think I should conclude, and thank you for your attention. Oh,
John, thanks a lot. Sorry.
I'm just going to show you the stars of the show. Now, if you look at the label here, it says zooplankton sampled from the Lake District. Windermere is the biggest lake in the Lake District, so I guess there's a good chance that these are the zooplankton that were doing their dancing and swimming and stirring. I think one final comment on that is that when you're watching this sort of thing, you tend to think that the scales of turbulence that they're generating will be too small, really, to do any effective mixing. But there's a paper in Nature which shows that in tanks like that, if you put a lot of them in together and measure the turbulence, it does develop larger scales. It's as if the vortices from the individuals somehow coalesce and make sort of inverse cascade, I suppose, is the picture that people have. We've tested our turbulence, and it's very difficult to see any difference in the spatial scales from that physical turbulence.
So John, thanks a lot. So there will be a lot of applause, I guess.
Oh, thank you.
This was a very thoughtful analysis of a non-oceanographic topic, but of course highly related to all the methods we are using in the coastal ocean. And I think there are lots of questions. Just raise your hand, please, electronically. That would be the easiest thing. Go on reactions, and then you can raise your hand. While people try to find out how that works, I might have one comment or question, maybe. I mean, this zooplankton, it might show some like swarm behavior or so, right? That it is not like random walk individually, but they could maybe sense the motions of the neighbors and maybe go up in groups or something like that, and then come up with the larger scales, right?
Yeah, I think that's a good point, actually. When you look at those pictures that show the swimming, the dots of yellow lines going up, and you don't see them coming down, it's as if they're all hungry at the end of their rest in the bottom boundary layer, and they're all rushing to get to the table to raise at the higher levels. And then when they're satisfied, they sink down more slowly. So yes, there is there could be some sort of cohesive group behavior that's involved.
Yeah. Good. I mean, I have many other questions, but I think I should give the floor to others, like Rocky, who has a question.
Hi, John. I'm sorry I came in really late, but that was really great, and I didn't guess what the answer to the riddle was going to be. And the one of the things that I've always wondered about with these is the sort of metabolic story. Like, you can, as a physicist, you can say what, how many watts per square meter, or how many watts these guys are actually consuming in their turbulence, and how much are they eating, and what fraction of their metabolism does this represent?
Yes, I think it was Peter Williams, actually, at Menai who drew my attention to the question you're raising, and said that you should be able to connect levels of dissipation in these bioturbulence situations with the amount of calories they're consuming. But some of that is, well, I wouldn't say it's well known, but it is known to some extent. So you can actually get from the physics to the biology and back again, I suppose. Yes, I think that's quite possible. I haven't actually tried it yet, but I think it should be doable.
Okay, Lars?
Yeah, John, so you talked about the stars of your show, right? These little zooplankton animals, and so you said they are small, but they can cause structures that are a bit larger than them, so you can see them with your ADCP. And the method you use, it relies on an inertial subrange. So it relies on energy put in at a large scale and being transported down to the smaller scales. But this seems to be more complicated, right? You have these small animals that jump around, and they may coagulate, they cause patterns. So how can we believe that there is an inertial subrange so you can apply your structure function method?
Well, we have tried actually to take that head on and look at, if, for example, when you're doing the structure function calculation, you have to specify a maximum range. And if you like, that's sort of asking about how big the eddies are that you're seeing. And when it was Brian Scannell who did this, when you do that, you can, if you change the Rmax, the maximum span that you're looking at in the structure function, you don't change the actual estimates very much at all.
All right. Okay.
But if there was a big scale dependence, then if you open the gate, made the Rmax much larger, then you would start to lose, the eddies would be smaller, so it would be weaker, so you would have less dissipation. I think it's a very important question though, because of course it could affect how much mixing is done as opposed to
exactly.
It's not the same thing.
Okay, thanks.
Next question is by Jen Ping.
Yeah, thank you, John. Very interesting talk. I feel very interesting to know about genetic dissipation. So question from me is that would this mechanism is a general phenomena in ocean as well, or is just a spatial mechanism in only the lake?
Well, no, it's rather the other way around, I think. There are quite a number of established cases of biogenic mixing in the ocean. I think Eric Kunzer is the name I remember as publishing one of the first articles about it in the Saanich Inlet in Canada. They found really very convincing evidence that quite large zooplankton there, I'm not sure of the species, but they were measuring dissipation levels, actually I think rather higher than we saw in the lakes. As far as I know, in the lake literature, which I've honed recently, there is no reports of, people have looked for possible biogenic dissipation, but not found it yet. So I would say that it's an open goal at the moment. I think there's a lot to be said for looking at this closely, and in particular seeing how it relates to vertical migration. I mean, the biologists have been studying vertical migration in the ocean as well as in lakes, but it's the very clear connection between them here, between that and the biogenic stirring by the zooplankton, which I think is the interesting thing.
Okay, thank you.
Okay, before someone else comes up with a question, I can jump in because I'm curious about one thing. I mean, your method, the structure function method, is based on the long beam velocity, right? And I mean the zooplankton is kind of pretending some long beam velocity of water, which is actually not there, right? It's just the motion of these plankton. So yes. Isn't that, I mean, shouldn't that influence your result, that you maybe get some divergence or something like that of a velocity along the beam, which pretends to be turbulence?
That's a very good question. I've heard it discussed before, and you know, in using ADCPs and acoustic techniques, generally Dopplers, we assume that we're seeing a backscatter signal that comes from the water, and as you're rightly implying, that isn't, especially in high concentrations. You know, if you're dealing with swarming behavior, that wouldn't be right. So I don't know the answer, but I recognize an interesting and important question. Presumably it's not too bad if the concentrations are not so large, because then you're mainly seeing the water. But in that tank, you sense that there was quite a lot of neighbor-neighbor interaction, and the acoustic beams would be seeing the motion of the. Maybe there's some. Yeah, I don't know whether the plankton speeds are actually related to the water speeds. I guess they are in some sense, aren't they? So, but whether they're biasing the structure function, interpreting them, I couldn't guess it, but it's an interesting point.
I mean, once you return to the lake, would it be possible to throw a microstructure profiler into it? Because that would completely ignore the presence of these moving particles, right?
Yes, I think so. I mean, I think Tom's already thought of doing that, actually. He was going to come at one stage while this project was going on, but we never actually managed to get around to it. But yes, because so many of them, well, before we started with this sort of stuff, most of the measurements were made with profilers.
Yeah.
And, Johnny Wostanco did a pretty good job with a long series of profiles from microstructure systems. But of course, it's no substitute for the continuous signal that we get from these mode instruments. But to do them together, yes, would have obvious advantages.
Okay, thanks, John. Jinping, is it another question of yours? No, okay. So I don't see a further question. So if there's a question, just shout, maybe.
Well, on that point of yours, Hans, the structure function method relies on the difference, I understand, between vertical velocities in adjacent layers. Now, these moving zooplankton, I guess, are moving more or less at the same speed from one layer to another. So I just wonder if that's a partial answer to your question, that it doesn't matter too much to the structure function method. But I'm not an expert in these things, but it just occurred to me that.
Sounds reasonable to me. Thanks, Dave.
And that's one of the great things about the structure function method. It is a difference, and it tends to get you out of trouble on a number of issues like that. Like for instance, whether you can measure turbulence properly from an instrument which is on a free-floating buoy in mid-water. And we thought at first that wouldn't really work, that the velocities the instrument would see due to the oscillation of the mooring, but you can get out of that very largely. The motions that are induced are actually perpendicular to the beams, pretty much, and so they cancel. Well, I forget exactly the argument, but the rotation is taken care of in one way, and the translation in another. And the beams actually do not actually reflect these induced motions that the instrument would see.
Okay, John, one of your co-authors has a question. Brian?
Not really a question, just a sort of comment. I mean, it took quite a long time to actually convince ourselves that we genuinely were seeing a turbulent signal, and it was only the conformance to the R to the 2/3 linear dependency for the structure function that actually certainly convinced me, then convinced John and others. I mean, we were basically looking at velocity anomalies up until that point. I think we have to be careful about assuming that a microstructure profiler would be the gold standard in this, because I suspect we must be looking at very high density clouds of some of those zooplankton. And if you drop a microstructure profiler down through them, they are going to be impacting on that microstructure profiler. So it's quite hard to figure out how do you actually get a real, an independent measure of this. And it sort of brings us back to the fact that actually we have a relatively small toolkit for observing turbulence. But it was an interesting exercise trying to convince ourselves that there was a real signal in this, and we were fortunate in that it was so well repeated on multiple days that that in itself provides a degree of supporting evidence. And I think what we must be seeing is kind of quite large scale turbulent eddies that are being created by the migration of these, which is a kind of a reversal of our normal thing. We normally think of a large eddy breaking down into smaller scales. Here we've got something starting small, building up, and then presumably dissipating down through the scales again. But it is quite interesting. You kind of want to get in there and see what's happening in a bit more detail.
Okay, thanks, Brian. Were there more questions? I mean, Lars looked like a question, or Reg, you have one?
Yep. Yeah, just a quick comment, really. That Rachel Carson, in her book, The 60s, The Sea Around Us, talks about the turbulence at the surface of the sea caused by biological upwelling. So it's very interesting to sit here and listen to you talk about measurements of the process. A quick question maybe would be, unless I missed it, I didn't hear you talking about the consequences of transverse seiching in the lake. I mean, Heaps did a huge amount of theoretical work on Windermere, I think it was, many years ago. And transverse seiching was part of that work, I believe.
Yes. And I mean, if the lake is very narrow, so it tends not to reflect rotation effects very much. But you can detect it, especially when the stratification is weak and the seiches are very long period. But it's not a big factor. One of the interesting things reflecting on that, which we observed when we first made measurements there, is that if you plot a scatter diagram of the longitudinal and transverse velocities in the mixed situation, then it's more or less circular. But as soon as the seiches start, then it becomes organized, and it's a rather narrow ellipse then. So that the motion is concentrated in the axial direction.
Yeah.
This perhaps isn't surprising, but it's still very striking when you see it.
Of course, the frequencies are so different from the two that it could be that the transverse effects have some relevance.
Yes.
Okay, do we have a final question? Just shout or show your hand. Brian, yours is old, right? Your yellow hand? Okay.
Brian's always got another question.
Yeah.
Yeah, well, John, you didn't talk a lot about the seiching. I mean, could you tell us a little bit about the seiches? I mean, it seemed like they have the velocities concentrated in the interface, so it looked like a higher mode, or?
Yes, there was quite a clear picture came out of that part of the work, actually. It amounted to the fact that only two modes were really important. The gravest mode, the lowest mode, was there a lot of the time, and the second vertical mode was there quite a lot. Actually, it made a significant contribution. But we looked for higher modes, and you really couldn't pick those out with any conviction.
Yeah. And the periods were diurnal, or what periods?
The periods, that was there's a diagram in the paper which shows how the periods of the seiches changes during the summer.
Okay.
Stratification, and they match almost exactly to the spectrally determined periods. So the first order internal wave theory is right. I think that's all approved, actually.
Okay.
There are some interesting things, though. I mentioned the diurnal forcing. I actually analysed the winds in the same way as we analysed the currents. And you can see a strong diurnal thing persisting through the summer. And it is actually, it seems to excite the seixas even when the natural period isn't right, when it's gone off resonance, do a strong forcing. The response is broad enough to allow some deviation from the internal wave theory.
Okay, thanks, John.
I was trying to resist the temptation. I didn't.
Okay. So thanks a lot for the good discussions, and of course specifically thanks a lot for the great talk to celebrate our VPOS, the first VPOS anniversary. The next VPOS seminar will be on April 21, and it will be Kerstin Schulz, former PhD student of Lars, and she will be talking about turbulent mixing and intermediate nephelolite layers in the Siberian continental shelf break. So we will go north from here. Okay. So if there's no more final comments, then we see each other in 2 weeks. And those who are here just for the PECS list, you can send an email if you want to be member of the VPOS mailing list to get all the announcements. Okay. Thank you.
Thank you.